Hello everyone, my name is Daniel Hauge and I will be presenting the work that I have been developing alongside Houston Hall with the guidance of Dr. Payne and Dr. Sartoli. Our research is titled malSET, an automated symbolic execution toolkit for assisting malware classification systems. But before we dive into more of the details for the methodology and implementation, it is important to understand why this research is relevant and important to the current landscape of research revolving around malware analysis and symbolic execution. To account for the growing sophistication of malware evasion and obfuscation techniques being utilized by malware writers and distributors, machine learning-based malware detection and classification systems have been growing in popularity as they provide better behavioral analysis of the programs they analyze than the static analysis incorporated in traditional signature-based systems that you would likely find in, say, a generic antivirus software. But for these machine learning systems to operate effectively, they require plenty of training data to construct the models that can effectively accomplish their designated task. There is also a lot of literature available for developing malware classification models, but little research has explored the utilization of symbolic execution for extracting behavioral characteristics from malware, even though the techniques have been heavily utilized in software vulnerability testing for years, if not decades. As for the methodology, we are utilizing the Anger binary analysis framework for its symbolic execution engine and suite of Python services for analyzing our malware samples to dynamically extract API and system calls as proven possible by 2 recent case studies on individual malware samples through the use of Anger. Therefore, this research aims to build on their success by developing an automated system that could extract both types of calls on a larger spectrum of malware samples. And as in our case, one of the primary data sets utilized for this research is provided through the 2015 Microsoft Malware Classification Challenge, which provides nearly 11,000 malware samples from 9 different malware families for the purpose of devising novel malware classification strategies. Now, if we look closer at the implementation section, on the left-hand side we have provided an example implementation of a short Python script utilizing the Anger framework to dynamically extract a key from progressively more complicated binary files, where a single short script like this is able to systematically explore a program to find the target information that we specify in the search parameters, which in this case was a simple key, but with a more advanced script could extract, say, a ransomware decryption key that could neutralize an instance of ransomware without having to pay the ransom fee to recover a system. Ultimately, our goal is to build upon this process to account for more complexities that are found within malware compared to their benign counterparts, and be able to provide an open source tool like we are in the process of developing and is shown on the right. But in order to accomplish this goal, we will need to account for the additional considerations brought on by our dataset and objective of the toolkit. To account for the path explosion challenge posed by Symbolic Execution Engine, our scripts must incorporate a more selective search strategy compared to BFS or DFS in order to limit the accumulation of execution states while ensuring that we still identify the binaries API and system calls. And as our dataset consists of malicious binaries, which vastly incorporates obfuscation techniques and potentially polymorphic mutation capabilities, symbolic execution provides a better possibility of detecting hidden characteristics than traditional forms of static or dynamic analysis. We will also be providing additional emphasis on the malware family SIMDA, as it was provided with significantly fewer samples to test which is very important to note because machine learning systems often require a certain level of training data to construct a reasonable model for their successful classification. Lastly, as this research is still in its preliminary stages, the next phases will include continued integration with Anger, with our dataset, and methodology required to further develop the proposed automated toolkit for malware analysis, followed by the evaluation of the improved machine learning accuracy gained by incorporating the behavioral characteristics extracted by malSET. If you are interested in keeping up to date with the progression of this research and the malSET toolkit, more details can be found at malset.com. Thank you for watching, and please let me know if you have any thoughts or suggestions.